Very frequently, when you're running a SN1 type reaction, what you have is some substrate, and that substrate gets dissolved in some polar protic solvent, and it is the polar protic solvent that actually serves as the nucleophile for the reaction. This kind of reaction, where the solvent is one of the reagents, tends to be called a solvolysis reaction. So what happens first? Well, we have a leaving group. The leaving group must leave. The result of this reaction, once again, is going to form a cation. This carbocation exists with some lifetime. That is to say, it sits there, it's relatively stable, it hangs out. In other words, you need to actually have a cation that's stable enough for this process to take place. The leaving group has to be good enough to leave. The cation that results has to be good enough to stick around for some lifetime. But once that carbocation has been formed, then your solvent may actually come by and make a bond to it. Alternatively, of course, the direct result of the chloride leaving is that you now have Cl- floating around. So there's a couple of options here. The Cl- could actually go ahead and attack again, and if it did that, you'd go back to where you came from. This is an equilibrium process. When this falls apart, you form a chloride and a carbocation, but these two things are charged, they're attracted to each other, and a very likely scenario is that they recombine. So this is an equilibrium step. However, sometimes the nearby methanol, and there's a lot of methanol around because this is the solvent, decides to come in and attack first before the chloride can. And if that happens, then we have another sort of equilibrium step where you now have a tert-butyl group and an oxygen has now made a bond to the cation that was there before, and the methanol is now bound. But of course, this methanol still has both the methyl and the OH present, so that makes its oxygen charged. So again, what we could do at this point is have the methanol leave and you could go back the way you came. On the other hand, methanol again is the solvent, so we have plenty of methanol floating around nearby, and it's eminently possible that a nearby methanol comes by and deprotonates this hydrogen, pulls off this hydrogen. Why would this want to happen? Well, the pKa for this is about -2, so this is a fairly strong acid. This is something that can happen just simply by collision. The result of the overall process is that now we have replaced the chloride with an O-methyl group. Again, the solvent serves as the nucleophile, and the product that we make incorporates the solvent in there. By the way, the other byproduct is going to be Cl-, and you could imagine that there's a proton left over that's floating around. For bookkeeping's sake, you could consider that to be HCl, but it's highly unlikely that the Cl- actually does the deprotonation because of the pKa values associated. So if we're going to diagram out the reaction coordinate diagram for this process, now you see that there's actually two intermediates along the way. So the starting material is still the substrate itself, the product is that product right there, and there's two places along the way where we have some intermediate energy. This one is going to be higher in energy than this one because this one lacks for full octet on the carbon, whereas this one has a plus on the oxygen. So the rough, very general sense for this reaction coordinate diagram might look something like that, where the initial well, intermediate 1, is the tert-butyl cation, and the well number 2, that would be instead the protonated species, where the oxygen has already added, but the proton has not yet been abstracted. Obviously, there are transition states at each one of these humps, and the starting material is over here on the left, and the product is over there on the right.